Imagine you are waking up in the rubble of a civilization that has just been completely wiped out. The libraries are burned, the servers are melted, and all our hard-won knowledge, biology, astronomy, engineering, is gone. Dust. You have time to carve just one sentence onto a stone for the survivors who might crawl out of the caves 1,000 years from now. Just one statement to help them rebuild everything we knew. What do you write? What single sentence contains the most information about how our universe actually works? I believe it is this. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. It sounds simple, doesn't it? Almost too simple. But if you have that idea, that the world isn't smooth, but granular, like a pile of constantly shifting sand, and you apply a little imagination, you can reconstruct almost the entire physical world. Let's play a game to see how powerful this is. Let's look at something boring. A drop of water. Just a splash on the table. To your eye, it's smooth. It's continuous. You can run your finger through it. But suppose we had a magical microscope, one that could magnify things better than any instrument we have today. Let's dial it up to 2,000 times magnification. Now that single drop is 40 feet across. It's the size of a large swimming pool. And what do you see? It's still mostly smooth water. But look, there are little football-shaped monsters swimming around. Paramecia. Fascinating, right? You might stop there and spend a lifetime watching the hairs on their bodies wiggle. But we are physicists today, not biologists. We want to know what the water is, not the monsters swimming in it. So, crack the knob. Let's go to 2,000 times magnification again. Now our drop of water is 15 miles wide. It covers a whole city. And now the smoothness is gone. You look down, and the surface isn't glass anymore. It's teeming. It looks like a football stadium seen from a blimp. A swarming, shifting crowd of billions. Turn the knob one last time. Magnify it another 250 times. Now we are looking at the fundamental grit of the universe. What do you see? You see particles, little blobs, and they are dancing. For water, these blobs look like Mickey Mouse heads, one big dark oxygen atom with two little white hydrogen ears. We call this a molecule. And the most wonderful thing is that they are not sitting still. They are jiggling, bouncing, twisting, turning. They are stuck to their neighbors, pulling on them like magnets. But if you try to push them too close, bam, they push back. They are promiscuous, constantly changing partners, but always holding hands. This jiggling, this perpetual dance, this is what we call heat. Now, imagine we heat the water. What does that mean in our atomic story? It means we turn up the music. The molecules dance faster. They slam into each other harder. Eventually, they are moving so fast that the glue, the attraction that holds them together, isn't strong enough anymore. They break free. They fly apart. This is steam. The molecules are now flying alone, smashing into the walls of the room like millions of tiny tennis balls. This is what we call pressure. Imagine you're standing against a wall, and a billion tennis balls a second are pelting a shield you're holding. You'd feel a constant push, right? That's all gas pressure is. The brute force of kinetic energy. Now let's go the other way. Let's cool the water down. The music slows. The jiggling calms. The attraction starts to win over the motion. Suddenly, they lock arms. They click into a rigid pattern, like soldiers in formation. This is ice. Notice something strange. In the liquid, they were packed tight, tumbling over each other. But in this rigid crystal formation, there are gaps, holes. The structure is open. This is why ice floats. It's one of the few things in the universe that gets bigger when it freezes. And even here, frozen in place, they aren't dead. They are still vibrating, shivering in their assigned seats. If you heat them just a little, they shake themselves free, the structure collapses, and you have liquid water again. Let's look at the surface of the water again. It's a chaotic place. Some molecules are moving fast, some slow. Occasionally, one molecule gets a lucky kick, whack, from its neighbors and gathers enough speed to break the surface tension and fly off into the air. We call this evaporation. And think about it. The one that left was a fast one. It took more than its fair share of energy to escape. So, what's left behind? The slower ones, the cooler ones. This is why blowing on your soup cools it down. You are helping the fast runners escape, leaving the slow, cold guys behind. Now let's drop a crystal of salt into our water. A battle begins. The salt is a fortress, ions of sodium and chlorine lock tight. But the water molecules are curious. They surround the salt fortress. The negative oxygen ends target the positive sodiums. The positive hydrogens target the negative chlorines. They wiggle and pry until pop. They pull the salt apart, carrying the ions away into the crowd. We can even make new things. Imagine carbon burning. A carbon atom and an oxygen molecule slam into each other. The oxygen snaps onto the carbon. Snap. This snapping together releases energy, kinetic energy. The new molecule flies off wildly. That motion is the heat of the fire. Everything, literally everything, is a dance of these little particles. The weather, the smell of violets, the salt in the ocean, the burning of a star. It's all just atoms, pushing and pulling, complying with these simple, beautiful rules. If you understand that, you have the key to the library of the universe. Isn't that wonderful? Have you ever sat and stared, really stared, at a glass of water sitting on a table? It looks so peaceful, doesn't it? A dead, uninteresting thing. You might leave it there for 20 years, and to our clumsy, giant eyes, it seems like absolutely nothing is happening. But that's just because we're too big to see the game. If we could shrink ourselves down, way, way down, 1 billion times smaller, and look at that surface again, we wouldn't see a calm, flat sheet. We would see a violent, chaotic storm. It's wonderful. Let's dive in and see what's really going on in that still glass of water. The storm at the surface. Imagine we are looking right at the boundary between the water and the air. Below us, the water molecules are piled together, jiggling and bumping into each other continuously. Above them, it's not empty space. There's air. We see nitrogen molecules, pairs of nitrogen atoms stuck together, oxygen molecules, and even some water molecules that have already escaped. That's water vapor. Now watch the water molecules closely. They are always moving, jiggling around due to their heat energy. But they don't all have the same speed. It's accidental. Every once in a while, a molecule on the surface gets hit just right, a lucky kick from its neighbors, and it picks up enough speed to break free from the attraction of the water below. Pop. It flies off into the air. That is evaporation. Molecule by molecule, the water is disappearing into the air. But wait, look at the air above. The water vapor molecules floating around there are also crashing into air molecules and bouncing around. Occasionally, one of them comes flying straight down toward the water surface, and smack, it gets captured again. It gets stuck. So, in that still glass of water, two furious processes are happening at the exact same time. Molecules are flying out, and molecules are crashing back in. Why does the water level look unchanged to us, Because it's a tie game, the number of molecules escaping is roughly equal to the number coming back. We call this equilibrium. To our eyes, nothing happens, but down there, everything is happening. It's a dynamic, churning exchange, constantly in motion. Blowing on soup. Now what happens if we change the rules? Suppose we take the lid off the container and blow across the top of the water. When we blow, we sweep away the moist air, the air full of water vapor molecules, and replace it with dry air. Now, the water molecules are still trying to escape just as fast as before, because the water is still jiggling, but there are almost no vapor molecules above to crash back in. The result? The traffic is one way. Lots of molecules leaving, very few coming back. The water evaporates rapidly. This leads to a fascinating question. Which molecules leave? Remember, to break away from the grip of their neighbors, a molecule needs extra energy. It needs to be moving faster than average. So, the molecules that escape are the hot ones, the fast ones. Who is left behind? The slow ones, the sluggish ones with less energy. Since temperature is just a measure of how fast the molecules are moving on average, the water that remains gets colder. This is why you blow on hot soup, to cool it down. You aren't just pushing the heat away, you are encouraging the energetic molecules to escape, leaving the colder liquid behind. It's an evaporative cooling machine, and it works the other way too. When a vapor molecule crashes back into the water, it is pulled in by a sudden, strong attraction. It speeds up as it slams into the surface, dumping its energy into the liquid and generating heat. So, molecules leaving takes away heat, cooling. Molecules arriving generates heat, warming. When the traffic is equal, the temperature stays the same. When you blow on the soup, you stop the return traffic and the cooling wins. Isn't that simple? The air getting lost. There is another side character in this drama. The air itself. While the water molecules are busy jumping out and diving in, occasionally a nitrogen or oxygen molecule from the air wanders into the crowd of water molecules. It gets bumped around, gets lost in the maze, and finds itself trapped inside the liquid. This is how air dissolves in water. It's just air molecules working their way into the gaps. If you've ever seen a glass of water sitting out, develop tiny bubbles on the side, or if you know why fish can breathe underwater, it's because of this wandering air. If you suddenly lower the air pressure above the water, those trapped air molecules rush to escape faster than new ones can get in, forming bubbles. This is the danger for deep-sea divers coming up too fast. The bends. The nitrogen dissolved in their blood tries to bubble out all at once. It's physics happening right inside the veins. The dance of salt now. Let's look at a different kind of process. What happens if we drop a crystal of salt into the water? A salt crystal is a beautiful, organized fortress. It's not made of neutral atoms, it's made of ions. An ion is just an atom that has an electrical charge because it lost or gained electrons. In salt, sodium chloride, we have chlorine ions, big negatively charged fellows. Sodium ions, smaller, positively charged ones. They stick together in a rigid cubic pattern because positive attracts negative. It's a very strong electrical bond. But water is a special substance. A water molecule isn't just a blob. It has a positive side, the hydrogen atoms, and a negative side, the oxygen atom. It's like a tiny magnet. When we put the salt in the water molecules gang up on the crystal. They surround the ions. The negative oxygen ends of the water point at the positive sodium. The positive hydrogen ends point at the negative chlorine. They tug and pull. The attraction of the water for the ions is often strong enough to overcome the attraction of the ions for each other. So, the ions jiggle loose. They float away, surrounded by their own little entourage of water molecules. This is what it means to dissolve. A battle for balance. Just like with evaporation, this isn't a one-way street. As the dissolved ions float around in the water, sometimes they bump back into the solid crystal. If they hit the right spot, the electrical attraction of the crystal grabs them, and they get stuck again. They crystallize. So we have another dynamic battle. 1. Dissolving, ions leaving the crystal, pulled by water. 2. Crystallizing, ions returning to the crystal, pulled by salt. If there is only a little salt in the water, the leaving wins, and the crystal disappears. If there is a ton of salt, so much that the water is crowded with ions, the returning rate catches up. Eventually, the rate of leaving equals the rate of returning. The crystal stops shrinking. We say the solution is saturated. Again, to our eyes, it looks like the salt just sits there at the bottom of the glass. But microscopically, it's a frenzy. Ions are constantly dissolving and recrystallizing, trading places billion of times a second, maintaining a perfect, delicate balance. Nature is never truly still. Even in a dead, silent glass of salty water, there is a universe of motion, energy, and conflict. It's all there, jiggling away, waiting for us to understand it. The atomic universe in a breath and a flame. Have you ever looked at a campfire and asked yourself, purely and simply, what is it? It creates a terrible commotion. This thing we call fire. To understand it, we must stop imagining atoms as dull, static billiard balls. Nature is not a museum of still statues. She is a vibrating, frantic, dynamic mess. When you see a log burning, you are watching a molecular catastrophe. Consider the carbon in the wood and the oxygen in the air. Oxygen atoms are social creatures. They like to hold hands in pairs. But when they get close to carbon, a switch occurs. The attraction to carbon is so strong that the oxygen snaps onto it with tremendous violence. It is a chemical crash. This snap is not gentle. It releases energy. The new partners, carbon dioxide or carbon monoxide, fly off, spinning and vibrating. They hit their neighbors, pushing and jostling them. This agitation is what we call heat. Heat is merely the kinetic energy, the motion of atoms. When you warm your hands by the fire, you are being bombarded by billions of invisible particles, accelerated by that violent atomic snapping. The light you see? That is just the visual evidence of the atoms crashing together with enough force to generate photons. It is stored sunlight, released in a chaotic dance. But nature is not just violent crashes. It is also delicate architecture. Imagine you are walking through a garden and you smell a violet. What is happening there? It feels like an illusion, a mood. But it is a physical reality. Pieces of the flower are literally breaking off and entering your nose. But these aren't simple little molecules like the ones in the fire. These are monsters. These scent molecules are complex pirate ships of atoms. Rings of carbon twisted and puckered, hydrogens waving like flags, oxygen tucked in the corners. The great triumph of organic chemistry is that human beings, without ever seeing these atoms, used logic and experiments to deduce exactly how these complex shapes are put together. It is a detective story of the highest order. Now, a skeptic might ask, if we can't see them, how do we know they are there? We can see their footprints. Look at dust particles floating in a glass of water under a microscope. They don't sit still. They jiggle. This is Brownian motion. The dust is being kicked around by an invisible crowd. The water molecules. The water is not a smooth sheet. It is a granular bombardment of atoms. The jiggling of the dust is the direct proof that the atomic world exists. And this leads us to the most staggering idea of all. If the rock is atoms, and the fire is atoms, and the scent of the violet is atoms, what about the frog? What about you? The most profound hypothesis in science is that everything animals do, atoms do. There is no extra spark, no magic ingredient. You are a pile of atoms, but do not let that word merely trick you. You are a pile of atoms organized with such breathtaking complexity that you can think, you can feel, and you can wonder about the universe you are made of. You are the universe looking at itself.
You have just experienced an adaptation of the first chapter from the legendary 1963 book, The Feynman Lectures on Physics. We are just beginning this journey through the laws of the universe. So please subscribe and turn on notifications. Your support is greatly appreciated.